Let's talk about Lagrange points. So, what are Lagrange points? That should be the first obvious question. In simple words, these are parking spaces in the universe where your car would be safe from gravity if you're capable of parking there. So, imagine you're looking for a place in space which is at a constant distance from the Earth and the Sun, and you would like to remain there for long. So, Lagrange point is the best suited place for you. Also, in other words, let's say your car is running low on fuel and you want at the same time infinite mileage with the remaining fuel that you have. Mileage is nothing but kilometers per liter. How much kilometers you can travel per liter of fuel. So, with the very minimum fuel, if you want to maintain a safe position relative to Earth and Sun for very long time, Lagrange point is the place for you. And this is what most scientific organizations are nowadays looking for in terms of satellite launches. For instance, James Webb Space Telescope is placed at L2 Lagrange point. Uh, Aditya L1, which is an upcoming space mission from ISRO, is going to be placed at L1. We'll come back to what L1, L2, L3, L4, L5 is, but Lagrange point is a very useful asset when it comes to space missions. And these are like magic points where effect of gravity from two different objects kind of cancels out. So let's look at more scientific explanation of the same. There are solutions for three body systems basically, which comes out as Lagrange points. And at these points, the sum of net forces becomes zero. So your acceleration is zero if you're placed at any of the Lagrange points. Acceleration in the sense there will be some angular acceleration because you're moving in a circle, but there won't be any linear acceleration, translational acceleration. So now let's look at what makes these Lagrange points. So for that we need to understand free body diagram. So in space, if you place an object, there'll be gravitational forces which will be acting. This is one of the forces. There's another kind of force which is centrifugal force. I'll explain this in the next slide, but in a simple words, if you're rotating an object, there is an outward force which acts uh, along radially outward direction, which is nothing but centrifugal force. And the inward force is centripetal force. Now, these two forces, so the summation of all the forces acting, in this case, typically there'll be these two forces, gravitational and centrifugal force. Two forces should cancel out and the net force should become zero. So that's the whole idea of Lagrange point. An object placed at Lagrange point remains stationary with respect to the other two bodies. So as I mentioned, it's a solution of a three body system. So the third body, which can be a satellite, other two bodies could be planets, stars, etc. So with respect to the planet and the star, the satellite would remain stationary, which is a very cool thing, by the way. So this is a brief about Lagrange points. Now let's go into a even more simpler explanation with some visuals. So let's imagine a system of Sun and Earth. So if you place the object too close to the Sun, as shown here, the Sun will attract it and the object would be pulled towards the Sun. Okay. Similarly, if you place the object too close to the Earth, the object would be pulled towards the Earth. But there will be a point in between these two objects where the gravitational force of the Sun and the Earth will cancel each other out. So in this case, at this point, and we are assuming that we are not talking about the centrifugal force yet. We are assuming that the Sun and the Earth are stationary. And if these two bodies are stationary, there will be a point, there will be a stationary point at some distance from Earth, at which the gravitational pull of the Earth will balance out the gravitational pull of the Sun. So that object will remain stationary there forever, unless there is any other external force which act on the system. So this three body system solution is nothing but the Lagrange point, and this point, by the way, is known as L1 Lagrange point. So this is L1. Similarly, there are four more additional solutions to this problem as shown in this image. So this is Sun, this is Earth, and then we have five Lagrange points: L1, L2, L3, L4, and L5. L3, L4, and L5 make a equilateral triangle. Now let's understand centrifugal force. So let's look at the image on the left. So you have you all must have seen uh, or might have done this. So basically, if you tie a ball or a stone at the end of a rope or uh, a thread, and you kind of rotate it, the thread produces a tension which kind of is trying to pull the stone towards you as you're trying to rotate it, but there is an outward force as well, and the balance of these two makes it rotate in a circular path. So the inward force is known as centripetal force, and the outward force is known as centrifugal force. Now this is true for a system which we are more familiar with the system we are more intuitively interacting with. But there is no string in the celestial objects, right? The Earth is not bound to the sun by a string. It's rotating because of the gravitational force. So the centripetal force, which was here produced by the string, in case of massive objects, is produced by the gravitational pull. So we don't call it centripetal force, but we'll call it gravitational attraction force. So our moon orbits Earth at, in a stable orbit. That's because the gravitational pull of the Earth is being cancelled out by the centrifugal force which is acting outwards. So the Earth is trying to attract the moon, but the centrifugal force which is acting, which is just a function of the speed. If an object is orbiting or rotating at a particular speed, it has a tendency to go outwards. That you can even relate to a stone, right? If you tie a stone and you kind of rotate it, it has a tendency of moving outwards. If you release the string, it will go outwards. So this is because you're trying to rotate it, and there'll be an angular acceleration outwards. So there'll be an angular acceleration which will eventually lead to an outward force. So the centrifugal force is being balanced by the gravitational pull of the Earth. That's why the moon is in the stable orbit. So is the case for Earth and Sun system. So the Earth is bound to the Sun by the balance of these two forces as well. Now, this centrifugal force comes into play when there is a velocity. In the previous slide, we saw a stationary example, but now in reality, the Earth is also rotating. So if you're talking about Lagrange points for Earth-Sun system, we need to consider rotational velocity as well. So a Lagrange point will be having the same rotational speed as Earth in case of Earth-Sun system. So all the Lagrange points L1, L2, L3, L4, L5 will have the same angular velocity as the Earth has with respect to the Sun. So now we are assuming it with respect to the Sun because the Sun is very massive as compared to Earth. So the CG is almost located at the Sun itself. So centrifugal force is the other force which we need to take into consideration while balancing out. Now because of this, you finally get 5 Lagrange points if you do the math, which we'll talk about in a later video. I'll try to also derive L1, L2, L3, L4, and L5 distances in a different video. But for now, to keep it simple, let's assume these 5 points are solution of of the force balance, which eventually turns out to be a zero at these locations. And the forces are gravitational force and the centrifugal force. So these 5 Lagrange points are clear to us probably. What is the difference between these five? Is there any Lagrange point better than the other? So the answer lies in stable and unstable equilibrium concept. So imagine this image. You must be familiar with this. It's an image which shows a ball on a hill and a valley. So we all know if we try to move the ball from this location slightly upwards, it will still come down to this position again. So this is stable position, stable equilibrium. Whereas the ball is at rest, which means it is at equilibrium, but if we move it slightly, then it will fall down to either of the sides. This is known as unstable equilibrium. And same concepts applies to Lagrange points as well. The difference with L1, L2, L3 on one side and L4 and L5 on the other side is that L4 and L5 are stable equilibrium Lagrange points, whereas L1 to L3 are L1, L2, L3 are unstable equilibrium points. Stables means if you place an object there and then move it a little bit, it will go back to where you place it. Unstable means the opposite. And now if you look at this image, it makes more sense. So this is an image showing the gravitational field. The places where we don't see lines is basically where the gravitational force of Sun and Earth cancels each other out. So here you can see L1 and L2 along with L3 are kind of unstable equilibrium points, whereas L4 and L5 are fairly stable. Having said that, it is important to note that even though Lagrange points are stable, but any these L4 and L5 specifically, but any such satellite being inserted into an orbit at these points still needs some amount of fuel to maintain its relative position because of the factors like gravitational perturbation, solar pressure, and other effects like irregular shape, non-uniform gravity, and effects of radiation pressure, which can affect its object over time, its orbit over time. So now, talking about, okay, we get what L1 to L5 is, but what are the distances? So here is the explanation for that. So we know we have these four solutions of the three body system where gravitational field cancels out along with the centrifugal force. So L1 is roughly zero point 0.01 AU. What is AU? AU is astronomical unit, which is equals to 150 million kilometers, which is almost the same as the average radius of Earth's orbit around the Sun. So it's basically the radius, if you consider the orbit of Earth to be approximately a circular orbit, then the effective radius that comes out is nothing but 1 AU or 150 million kilometers. L1 is at R by 100, which is 0.01 AU, which is nothing but 1.5 million kilometers. L2 is same as L1, but on the other side. So it's on the other side. Here, if you do a force balance, you'll get the same distance. So if you want to know in a high level what L1, how to calculate L1, basically what you need to do is consider the gravitational force G m1 m2 by r square formula to calculate gravitational force due to Sun, gravitational force due to Earth, and then you we so the concept is Lagrange point has the same angular velocity. We know the angular velocity of Earth. Once you know that, you can calculate the centrifugal force, which is nothing but mr omega square. So the radius would be the distance from the CG, which is the distance from Sun, times mass of the object times the square of angular velocity. If you do the math, sum up all the forces, make it equals to 0, you'll get the distance. Now L2 is same as L1. L3 is 1 AU. So L3 is on the other side of the sun. Now since 99% of the mass of the entire solar system lies just inside the sun, so it's obvious that the gravitational pull of the earth would be negligible if you make the distances comparable. So now here the L1 and L2 points, although this image is not to scale, but it's fairly close. You can see it's R by 100. So 1/100th of the distance between Earth and Sun is where the L1 point is located. So it's fairly close. If we make distance comparable when we're calculating gravitational force, Sun will be a clear-cut winner. So at L3, the distance from Sun is 1 AU. The distance from Earth is 2 AU. So clearly the gravitational pull of the Earth would be negligible. Hence we can assume that it should be at the same distance. If it has the same angular velocity, it should be at the same distance from the sun as the earth is. That's why earth has an orbit of that radius, right? So L3 is 1 AU, L4 is in between 0.13 to 1.89 AU. This is because L4 and L5 are stable equilibrium points. So it's not a point. Basically it's a it's an area of space where you can place your satellite or any celestial object. And so would be the case for L5, and it maintains symmetry. So L4, L3 and L5 forms an equilateral triangle. These are the distances from for Earth Sun Lagrange point system. Similarly, Earth Moon will also have a Lagrange point solution, right? It's a solution between any two objects which are massive enough to have a significant gravitational impact. So now these are the distances for Earth Moon system which you can look at. I'll not go into the details, but I hope this video was helpful. That's all about Lagrange points. Thanks for watching.